All right. Hello, everybody. So happy holidays to all of you. Um, I want to say thank you, of course, again for all the support. So I'm on break right now, and I wanted to, do something for everybody, of course, and I've had a lot of requests for doing a follow-up video because the indexing diffraction patterns for the cubic lattices and the cubic crystals was so popular. I've had a lot of questions or inquiries about doing one for hexagonal unit cells. So that's what we're going to do. So, and this is going to be pretty ambitious here, but hopefully, I'm going to throw enough information at you here that there'll be some good stuff for you here. So we'll have a bit of an adventure today. I do apologize. I am kind of battling a little bit of a cold here, so I might sound a little more hoarse than normal, but right? Show must go on. So without further ado, let's go ahead and get started here. So let's see here. Oh, come on. Well, that's not a good start. Okay, there we go. All right, so just a brief review about indexing DPs. Okay, so we have, so this is a simulated DP from a diamond cubic crystal. You can probably, take a look at the symmetry here and guess what the zone axis is. So, and you can see in the upper right here, these are the allowed HKL reflections and the relative G vector lengths. And this is obviously just a partial table, but this is the shortest G vector and then increasing as you go down. Okay. So again, the process is we have to of indexing a DP is we have to figure out the zone axis and we have to figure out the indices for the spots. Okay. So to do this, we have to first identify an orthogonal pair of G vectors. Okay. And so orthogonal, of course, means that mathematically they dot to zero. So by convention, I prefer to arrange it so G1 is the shorter of the two if they have to be different lengths. Obviously, we saw examples where they can be the same length, right? Like with the 001 zone axis family. But in the case, in the majority of cases, that's not going to be the case. So I prefer to keep G1 the shorter of the two G vectors. And remember, the convention is that the zone axis points out of the page, right? So then I also arrange it so that we have G1 cross G2 that points out of the page. And so that gives us our zone axis, okay? So we identify an orthogonal pair, and then we know from the camera equation that if I measure the physical lengths of the two G vectors on the diffraction pattern, right? Meaning I measure it in millimeters or I measure it in inches or centimeters or whatever. If I take the ratio of those, then I get the actual ratio of the G vectors themselves, okay? And again, right, we're assuming that we know what the structure is to begin with, which is what's going to be the case the vast majority of the time, right? The vast majority of the time, you're going to have an idea what you're dealing with beforehand, right? So all we need to worry about in the case of a cubic crystal, right, is the relative G vector lengths. We don't have to, concern ourselves with the absolute lengths, okay? So again, we get a calculated ratio, or I'm sorry, a measured ratio, and then what we need to do is we need to compare it with some calculated G vector quotient values. I'm sorry, I mean to say, right, this is a quotient, not a ratio, so try to be consistent with that as much as I can. Okay, so this is an example of a G1, G2 table that has been calculated. Okay, so again, using, right, this same 6 G vectors that we've put in the table. Okay, so I want to spend some time going over this because I didn't exactly do a very good job with this in the previous video. Okay, so what we see here in this table is that we have 6 columns, okay? So if we look at the first column, what we are doing here is we are starting with the assumption that G1 is equal to the first G vector in the G vector list, okay? Now by first, I mean the shortest one. So that would correspond, right, to this guy right here, okay, to the 1, 1, 1, okay, with this relative G vector length, okay? Then what we're doing is we are dividing that G vector by all the other G vectors in the list, okay? So we're going to take this G vector length and divide it by itself first. So that's going to give us 1. Then we're going to divide it by the next. So that's going to be less than 1. Then the next, which is going to be a little bit less. And then the next, which is going to be a little bit less. So basically, every other term beneath the first one will be less than 1. Okay, and it will be decreasing. Okay, and that's exactly what we see here. So then if we go to the, right, just a synopsis, right? So then if we go to the second column, we're now assuming that G1 is the second G vector in the allowable list of G vectors, and we're doing the same thing. We're dividing that G vector by all the other G vectors. So again, when we get to the same G vector, our quotient will be 1, but if we look at the preceding one, because now that G vector is shorter than the one that we're assigning for G1, that value will actually be greater than 1. And then as we go below, those will all be less than 1, okay? So what we see here is, because we cut off the table at 6, we have a 6 by 6 matrix here. All my diagonal elements are 1, right? And then above the diagonal, I have quotients that are greater than 1, and then below I have quotients that are less than 1, okay? So we can generalize this for the nth column, right? We let G1 be the nth possible G vector, okay? So again, that would be the nth longest G vector, okay? We're dividing that G1 then by every other possible G vector, and that's what we're getting in the nth column, okay? So we use the example here of the first, the second, the third, right? This would be the fifth, right? We're assuming G1 is the fifth. We're dividing that G vector through by the first G vector, then through by the second, then through by the third, the fourth, and so on, okay? And when we get to the fifth, right, we're getting 1, okay? Okay, so then we have to check the table for matches that are close with the observed or the measured ratio, okay? So when we do this, right, I mean, you can go back and do this. We get, only one close hit here, okay? Again, I say close matches because you can have, a little bit of wiggle room depending on how you measure it. So it doesn't have to be perfect, but this is the only close match we get here, okay? So then what this tells us, okay, since we're in the second column and the 6th row, this tells us that G1 corresponds to the second G vector in the G vector list, and G2 corresponds to the 6th G vector in the G vector list, okay? So if the hit would have been, say, here, that would mean that G1 would be the 3rd G vector in the list, and G2 would be the 4th G vector in the list, okay? But that's not the end, right? Then what we have to do is we have to do some vector math. We have to make sure that we can get the two indices to dot to 0. We have to make sure that the spots are consistent with how we assign the indices, okay? And then if all that is copacetic, then we can calculate the zone axis from that, okay? And then we can go back, we can apply soft rules if we want to, okay? So that's just a very brief reminder about the indexing process that we used before with the cubic crystals. And it's no different when we move to the hexagonal crystal in a lot of ways, okay? There's just some additional nuances, but we're going to use this same methodology of finding orthogonal G vectors and then calculating a ratio and then calculating this table. That's not going to change, okay? Okay, so moving on to the hexagonal lattice. This is, I'm sure, basic stuff for most of you, but this is what we refer to when we refer to a hexagonal lattice. Is we have unit cells that have this dimension, okay? So we have our 6 lattice constants here. A equals B not equal to C, A equals beta, or alpha equals beta equals 90 degrees, and gamma equals 120, okay? This is a hexagonal lattice, okay? So I'm making the distinction between a hexagonal lattice versus a hexagonal unit cell, okay? So this is the lattice, and then when we apply a basis to it, when we get a unit cell. So if we want to look at a couple examples, we have hexagonal close packed. This is one of the most common hexagonal structures that we see. So this is a hexagonal lattice with a 2-atom basis. So if we put the same atom at these fractional coordinates with respect to the lattice vectors, okay? So that's the lattice below. And then if we add in the basis, this is what we get, okay? So we have atoms at all of our corners, and then we have an atom that is at projected along 2/3 of the A constant, then 1/3 along the B constant, and then halfway up along the C constant, okay? That's this atom right here. So that's what gives us the hexagonal close packed structure, okay? The other one is wurtzite, okay? So this is now very similar to the hexagonal close packed, except now it's a 4-atom basis, okay? So now we have 2 different atoms. We have A atoms and B atoms. So we have the original basis for the hexagonal close packed, but then we're adding another atom basically above every other atom that was already there, okay? Which is what we're going to see here in a minute. So basically, we're just adding an atom on top of a B atom on top of every A atom, just displaced upwards by 3/8 of the C axis. Okay, that's the easiest way to explain it. So probably the most common material when we think of wurtzite is probably gallium nitride, but there's plenty of materials that take this structure. And again, it's a compound, right? Because you've got A and B. You have aluminum nitride, you have zinc oxide. You know, there's a long list of these. Okay, so there's our hexagonal lattice, and there's our lattice plus basis gives us a unit cell. Now, one thing I would like to point out with wurtzite, unlike hexagonal close packed, does not have inversion symmetry, okay? So I could have just as easily designated the B atoms to be where the A atoms are and the A atoms to be where the B atoms are. That would be a perfectly valid way to define the unit cell, okay? So as a result of the fact that, and that's because, right, the unit cell doesn't have inversion symmetry, okay? So because of that, this structure, it has polarity to it, okay? This is not something that we can actually directly observe in the parallel beam diffraction patterns, right? But if you saw the video I did on seabed, right, this is where seabed comes in, and we can use that to actually reveal things like the polarity, okay? But this is actually technically one of 2 valid ways to define the wurtzite structure. So we would actually call this, because, right, we would call this, if we're assuming that the blue balls are nitrogen and the green are gallium, we would call this nitrogen face, because the nitrogen atoms are on top of the gallium atoms, and those are facing upward. We would call that nitrogen face. If we flip the unit cell upside down, then we would have gallium face, okay? And we can do that again because the structure lacks inversion symmetry, okay? Okay, so then another thing to mention, if we go back here, let me go back a few clicks. Okay, if we go back to this HKL table and the G vector links, okay, we're going to get to this in a little bit, but these are the same for HCP and wurtzite, okay? There's no difference between the 2 of them, okay? So that's something that we can make use of here when we're doing our indexing later. Okay, so now indexing hexagonal unit cells. Okay, so we could stick with the standard 3-index notation, and that is still perfectly valid. You can use that for any structure that you want, but it's standard to switch from 3 to 4-index notation when you're dealing with hexagonal unit cells. Okay, now one thing I want to mention quickly is, notice I said hexagonal unit cells, okay, not hexagonal crystals. There's a difference between a hexagonal unit cell and a hexagonal crystal. For a crystal to be classified as hexagonal, it has to have certain symmetry elements, okay? But a crystal that has a hexagonal unit cell may not actually qualify as a hexagonal crystal, okay? A good example of that is sapphire, okay? Sapphire is defined with a hexagonal unit cell, but it is actually a trigonal crystal, not a hexagonal crystal, because it doesn't have the necessary symmetry elements, okay? to be classified as a hexagonal crystal. It's actually classified as a trigonal crystal. Okay, so I try to make the distinction between, you know, a hexagonal unit cell / lattice and a hexagonal crystal where appropriate. Okay, so HCP and wurtzite are both hexagonal crystals. Okay, so that's an important thing to delineate. Okay, okay, so then when we switch from 3-index to 4-index notation, this is what we get. So the planes, we add in this fourth index called I, which slips in there between the K and the L. And as far as G vectors, we now use the same thing, okay? Because G is normal to the planes, so we slip that I index there between the K and the L for the G vectors. As far as the directions, we now go from UVW to U prime, V prime, T prime, W prime. Okay, so now you notice I put primes there as opposed to just keeping the originals, and there's reason for that with the directions that we're going to see. Okay, but again, we slip that T prime in between the V prime and the W prime. So why would we go through all this hassle? Well, the reason is because of symmetry. Okay, so doing this makes it more obvious to see the crystal symmetry. So an example of this is if we look at 1, 2 bar 0 and 1, 1, 0 planes. So if we were looking at those in the perspective of a cubic crystal or a cubic lattice, those would obviously not look like they were in the same family, okay, obviously, and that would be correct, okay? So at first glance, these might appear to be, you know, different sets of planes from different families. But if we convert these to 4-index notation, what we end up getting is 1, 2 bar 1, 0, and 1, 1, 2 bar 0, okay? So it turns out these are in the same family, and by converting to 4-index notation, it makes the symmetry more obvious, okay? So that's why we use the 4-index notation, okay? So the takeaway here is that when you have hexagonal unit cells, you should index them with 4-index notation. Okay, so now converting from 3 to 4 index, as far as the planes and the G vectors are concerned, this is very straightforward, okay? So all we have to do to get that I index is just add H to K and then take the opposite, okay? So 1, 1, 0 becomes 1, 1, 2 bar 0, okay? So same thing with the G vector, right? Because G is normal to the plane. So I do the same thing, right? If I have the HKLG vector, I'm just adding H to K and then taking the opposite, and that's becoming I. The directions are a little bit more involved. So to go from UVW to U prime, V prime, T prime, W prime, okay? So we have to use these formulas here, okay? So we're starting, so for the U prime, we have 1/3 times quantity 2U minus V, and then for V prime, we have 1/3 times quantity 2V minus U. T prime is the opposite of the sum of U prime and V prime, or alternatively, you could call it opposite of 1/3 times the sum of U and V, and then V prime is, then W prime is equal to W. And then if you have fractions, of course, right, you have to multiply those through to get rid of them. Okay, that we'll see. So then what about if we have 4-index, but we want to go back to 3? Okay, so again, with the planes and the G vectors, this is very easy. Okay, so all you have to do is just drop the I index and leave HKL as is. Okay, so 1, 1, 2 bar 0 becomes 1, 1, 0. Okay, and that's very easy. Okay, so for the directions, this is not terribly difficult either, okay? So you have U equals U prime minus T prime, V equals V prime minus T prime, and then W equals W prime. And then again, if you need to reduce those indices down to the lowest, you know, multiples you can, okay? So you can use this as an example, okay? So 2, 1 bar, 1 bar 3 would become 1, 0, 1, okay? If you do the math, okay? Again, the final solution will be in 4-index notation. You might ask, well, why would we ever go from 4 to 3? You're going to see why in a little while, because we need 3-index notation when we're doing a lot of the vector math, okay? So then really quickly, I didn't do an example here. So as far as the directions are concerned, okay, if there's a bunch of examples you could work through, okay? If I wanted to convert the 1, 0, 0 direction, okay, that would actually convert to 2, 1 bar, 1 bar, 0. okay? That would be the appropriate direction for index notation, okay? So you could do that yourself and verify that when you have a minute, okay? We're going to work through plenty of examples of this, right, as we're going through this, okay? Okay, so now we talked about when we're indexing the DP, we need to find an orthogonal G vector pair. So now we need to define a G dot G for hexagonal lattice with arbitrary A and C constants. So if we do this, this is the equation that we get, okay? So this is our dot product for two HKL G vectors, okay, in a hexagonal lattice with A and C lattice constants. So if we make some simplifications here, so if we assume that we have a hexagonal unit cell that has a CA ratio that is square root of 8/3, okay, this is what we get when we are close to what's called ideal HCP or wurtzite, okay? And if you actually look at the CA ratios of a lot of HCP and wurtzite structures, what you find is that they do have a CA ratio that is very close to this, okay? So if we do this, we can actually do a few things, okay? So we're going to get to the dot product in a minute, but we can actually also define now G vectors independent of A and C, okay? So this is the equation for the G vectors in a hexagonal lattice, okay? Assuming, right, we have a CA ratio that is square root of 8/3, okay? So a little bit different than what we see for a cubic lattice, but you can see a lot of the similarities there. And again, this is independent of A and C, okay? So as far as our perpendicular G vectors is concerned, right? So we can substitute in the A over C in the above equation, right? And we end up getting this, okay? So this is our equation for the dot product of two G vectors in a hexagonal lattice, again, assuming that the CA ratio is equal to 8/3 to the square root of 8/3, okay? My apologies there. Okay, so now one of the things we saw with the cubic lattice is that we have this nice parallelism between real space and reciprocal space, okay? That's not always going to be the case. So one of the things we have to answer, especially when we're indexing non-cubic crystals, okay? So if we have a given lattice vector, what set of planes has that lattice vector as a normal direction, okay? Or alternatively, you could ask the equivalent question, what G vector is parallel to a given lattice vector, okay? You could also start with a given HKL set of planes, and you can ask what lattice vector is normal to them, okay? Or you could also phrase this as what lattice vector is parallel to a given G vector, okay? So if we have cubic lattices, and this only applies to cubic lattices, we have this really nice parallelism where HKL directions are always perpendicular to HKL planes, and HKL G vectors are always parallel to HKL lattice vectors, okay? That only applies in a cubic lattice. And we're actually going to prove this mathematically in just a minute here. So what happens, though, if the lattice is not cubic, okay? We have to use some math here to help us out and make use of something called metric tensors, okay? So try not to be too intimidated here, but it's not too bad here, but we're going to see some matrices in a minute here. But this is what allows us to answer these questions, okay? So we're going to start with what's called the direct metric tensor. So what this does is we start with a lattice vector, okay? We want to answer the question, what HKL set of planes has a UVW lattice vector as a normal direction, okay? Or phrased differently, right? What G vector is parallel to a given UVW lattice vector, okay? So this is the equation, okay? So the 3x3 matrix in the middle, that is your metric tensor, okay? So you're multiplying the metric tensor by the UVW vector, right? And you're getting out an HKL, okay? So this is how you answer that question, okay? So we can see now, if we're assuming a cubic lattice, right? All my off-diagonal terms are going to be 0. all my diagonal terms are going to be equivalent. So basically what I end up with is I end up with a scalar multiple of the identity matrix, okay? So this is the mathematical proof that you have the perfect parallelism, okay? Right, so hopefully that's very obvious to see, okay? And again, this is generalized for any unit cell, right? We could, generalize this for anything, okay? But specifically, right, we can see the parallelism for cubic here. And now we want to ask the reciprocal question, which is, I'm given a set of HKL planes. What UVW direction is normal to them, okay? Or phrased differently, what UVW direction is parallel to a given G vector, HKL G vector, okay? So we have a similar equation, okay, where we have a similar 3x3 matrix. So we're multiplying this 3x3 matrix by the HKL vector, right? The G vector in this case, and we're getting out UVW, okay? So we can again see, right? So the primes here indicate the reciprocal lattice constants for our unit cell, okay? And we can again see, right, that what we would end up getting here is all my off-diagonal terms would be 0. My diagonal terms would all be the same. So I end up with a scalar multiple of the identity matrix. So I have the same perfect parallelism, okay, between real and reciprocal space for a cubic lattice, okay? All right, so now, excuse me, what are we going to do with a hexagonal lattice, okay? So there's actually some nice equations for 4-index notation, okay? So we're given a 4-index direction. We want to know what set of planes has that as a normal direction, okay? Or what G vector is parallel to the given U prime, V prime, T prime, W prime direction, okay? So this is what the direct metric tensor looks like, okay? So, so we can see, right, we have a CA ratio there in the bottom, okay? And then we can, of course, right, since we know we're assuming we have an ideal CA ratio for ideal HCP or wurtzite, we could substitute that in if we wanted to, okay? But this is what we get for a hexagonal lattice in general as a direct metric tensor, okay? So then if we do the same thing for a reciprocal metric tensor, we have a given HKL set of planes, and we want to know what U prime, V prime, T prime, W prime direction is normal to them, okay? Or again, phrased differently, what U prime, V prime, T prime, W prime lattice vector is parallel to a given G HKIL vector, okay? So very similar looking equation here, okay? So basically everything is the same between the two metric tensors. The only thing that's different is this last term in the diagonal, okay? So in the previous equation, right, you had a 2 times C over A squared, right? And then in the reciprocal version, you have a 9/2 times A over C squared, okay? But all of the other terms are the same, okay? And obviously you have this prefactor in front, which ends up basically canceling out anyway and not really even being needing to be considered anyway. But that was put in there because that's what I remember copying from the textbook, okay? But this is how we can go between, okay? If we need to know a direction that is normal to a set of planes, or we need to know a set of planes that has such and such as its normal direction, okay? So using these metric tensors, we can make some useful generalizations for the hexagonal lattice, okay, to help us out and to help us quickly, help us quickly analyze situations and, get through the process of indexing, okay? So let's say we have directions, G vectors, and planes of this form, right? Of HKI0 form, okay? So what we can show is that we always have HKI0 directions parallel to GE HKI0 G vectors. And we always have HKI0 lattice vectors perpendicular to HKI0 planes, okay? So examples of this, right? So if I have 1, 1 bar, 0, 0, lattice vector, that is always parallel to G1, 1 bar 0, 0, and the 1, 1 bar 0, 0 lattice vector is always perpendicular to the 1, 1 bar 0, 0 planes. Okay, you can do the example below that and show the same thing. So then if we go to the next generalization, and this one is usually pretty obvious, if we have 000L forms of the same three components, then we have the same thing. Okay, so 000L directions always parallel to G000L vectors, and 000L directions are always perpendicular to 000L planes. Okay, and that's very obvious, I would think. Okay, so we can use 0001 is always parallel to G001, and 0001 direction is always perpendicular to 0001 plane. Okay, and then the last generalization, and this of course is not technically every generalization possible. These are the main ones we're going to make use of, though. Let's say we have two G vectors, and we know that the L component of each of them is not equal to 0. Okay, what we can show is that it is impossible to get a 0 dot product between these two G vectors. Okay, so again, one of the things we're doing, right, when we're indexing the DP, we're looking for an orthogonal G vector pair. We can use this to help us rule certain possibilities out. Okay, so if we have two G vectors and both of the L components are not 0, we can never have a 0 dot product. Okay, so these two G vectors can never be perpendicular. Okay, so again, something to make use of here when we start looking at the patterns. Okay, all right, so a few other things here. So if we want to talk about zone axis now in 4-index notation, so we have to use, right, so we know that crossing two G vectors in the diffraction pattern will give us the zone axis. We have to use 3-index notation when we're doing cross products. Okay, so we have to convert the G vectors to 3-index and then compute the cross product. Then we're going to get the result in 3-index notation. Okay, so this is what we have to do right here, right? Standard cross product. Okay, this is valid, by the way, regardless of your lattice type. Okay, you could do this with a triclinic crystal and your answer will be valid. Okay, this works whether it's hexagonal lattice, monoclinic lattice, cubic lattice, whatever. Doesn't matter. You could show this mathematically, which would be maybe a neat video to do, but I'm not going to do it here. Okay, then what we have to do is we have to convert B to 4-index notation. Okay, using the formulas that we established earlier. Okay, so really quickly we could ask a question like this. So what zone axis contains the 303 bar 0 and 02 2 bar 0 planes? Okay, or equivalently we can ask what zone axis is perpendicular to G303 bar and G02 2 bar 0. Okay, so you can do the math and, right, you can find out very quickly that your answer, depending on how you do the cross product, is either 0001 or 0001 bar. Okay, again, this is a direction, not a plane. We want to use square brackets here. Okay, so again, we would reduce G303 bar 0 to G300, and we would reduce G022 bar 0 to G020, right? All we have to do is drop the third index, okay, to go back to 4-index notation. Okay, again, remember, right, with zone axes, you're using the lowest possible integers. Okay, so 1, 1, 2 bar 2 would be correct. Incorrect would be something like 3, 3, 6 bar 6. Okay, notice also with a hexagonal lattice, your third index here, if you do this correctly, should always be the sum of the first two indices and then the opposite of that. Okay, so I should say that again. Okay, if you do this correctly, your third index with a hexagonal lattice should always be opposite of the sum of the first two indices. Okay, we can see that's what we have here. So if this was a 3, if we had 1, 1, 3 bar 2, then we know we did something incorrect. Okay. Okay, so now containing plane for a hexagonal lattice. Okay, so again, we have to use 3-index notation here. Okay, so the idea here now is if we have two directions, we want to know what plane contains them. Okay. Alternatively, if we have two directions or lattice directions, lattice vectors, we want to know what G vector is normal to them. Okay. So we have to first convert them to 3-index notation, and then we have to compute the determinant. Okay. This is very similar to what we did in the previous slide, right? Except now we're using lattice vectors to give us a G vector. Okay. And again, it can be shown, right? This is valid for any lattice type, not just cubic and not just hexagonal. Okay. Okay. So again, right? We get out our answer. It's going to be in 3-index notation. We have to then convert to 4-index notation, which is really easy because we just do opposite of the sum of the H and the K indices. Okay. So as an example here, so if we have what HKIL plane contains 2 1 bar 1 bar 0 and 1 2 bar 1 0. Okay. Or equivalently, we're going to ask what G vector is perpendicular to 2 1 bar 1 bar 0 and 1 2 bar 1 0 lattice directions. Okay. So if you do the math, right, you end up with 0001 or 0001 bar. Okay. Or some multiple of those, right? Possibly. Okay, again, this is, now remember, this is a plane, not a direction. Okay, you're using parentheses here. Okay, and now what we're going to see is that we may, depending on what we're doing, right? This is not a zone axis. We may need to adjust the indices to as needed, so we get, you know, the proper values for the spots. Okay, so you'll see where this comes into play when we start indexing some of the patterns. Okay. Okay. Then the last thing is the Weiss zone axis law, right? So the Weiss zone axis law states that if a plane is contained in a zone axis, the dot product of the normal with the zone axis should be 0. Okay, so that would be G dot B is 0, right? Every single one of the spots in the 0 order Laue zone in the DP should conform to that, right? So if we have HKIL plane and a U prime, V prime, T prime, W prime zone axis, okay? So if we have a dot product that's equal to 0, then we know that the plane contains that zone axis. So thankfully, though, we're not limited to 3-index notation here. Okay, we could do this with 3-index notation, but this also works for 4-index notation. Okay, so we can do 4-index dot products, and that will also be valid, just like it would be with the 3-index notation. Okay, so just as an example, if we look at the 4 to 6 bar 2 plane, does that dot to 0 with the 1 bar 2, 1 bar 3 direction? Okay, and so just looking at this very quickly here, the answer should be yes. Yes, it does do that. Okay. And again, right, you can convert those back to 3-index notation. Okay. So if you converted 4 to 6 bar 2 bar back to 3-index, you would get 4 to 2 bar. And if you convert 1 bar 2, 1 bar 3, you would end up getting 0, 1, 1. That should be your answer. Okay. And then you can verify, right? 4 2 2 bar dots to 0 with 0 1 1. Okay, so it's consistent both ways. All right, so now we're going to get into now indexing some of the DPs. Okay, so we have here, we have the DP, obviously. We have the spot here where we're going to indicate the zone axis once we've solved it. And then in the upper right here, we have our table of G vectors and our calculated relative G vector lengths. Again, we're assuming that we have ideal HCP or wurtzite here. Okay, so we have both 4-index and 3-index notation here to help us. Okay, so just looking at the pattern here, what would you say we have, right, in terms of the point symmetry? So to me, that looks pretty obviously like we have 6 mm point symmetry. Okay, so this is very similar to what we would see with like a 1-1-1 zone axis with a cubic crystal. In fact, it's identical. Okay, looking at this versus something from a cubic crystal, we would have no way of knowing that this was not from a cubic crystal. Okay, we only know that because we knew the structure ahead of time. right? So again, the way to prove that mathematically, right, is you can measure the angle between, right, the closest G vectors, and you should find that these are all 60 degrees, and these are all equidistant from the direct spot. Okay, so let me go back here and escape. Whoops, not escape. Okay, let me go back here and escape, and let me hide meeting controls. Okay, let me come back. Come on. All right, so point symmetry. We'll do 6 mm. Okay, so just as a guess, right? If we wanted to guess the zone axis, I think we'd all agree, right? Zone axis here is probably going to be 0001, or its opposite. Okay, I mean that's very obvious, right? In terms of hexagonal. Okay, so we really already do know the zone axis here. Okay, but we're going to go ahead and prove this mathematically. Okay, so just like we did before, we have to measure G vectors. Okay, so what I'm going to do is I'm going to make this guy my G1, okay, and this guy be my G2. So I'm going to measure now. Let me insert here. Shapes. Okay, so I have 6 G vector links right here. Whoops, going on. Okay, there we go. Okay, so let's see here. Draw, no, insert shape. Okay, I'm going to click and drag right there. Okay, there's my 6 intervals for G1, and then I'm going to do the same thing for G2. Let me just copy this. Let me make these a different color. Easier to see. Red. Okay. There we go. All right, and then let me make the ending of these the same. Arrows. Arrows. There we go. Okay, so now I only have 2 increments for this guy. Okay, so I don't have the ability to make 6 of them here. Okay, so let's try and do this as accurately as we can here. We're trying to get that in the center of the spots. That's pretty close right there. Okay, let's move this down a little. Okay. Okay, and that looks pretty good. Okay, so we have here picture format. Okay, is it going to tell me this? Okay, so we have 5.89 for divided by 6 for R1. Okay, so I'm going to come back to my MATLAB program here. Okay, and I have my program here that I used in the cubic example, which works just as well here. Okay, so I'm going to find where okay, so here we go. So I have 5.89, and my number of increments is 6. Okay, and then I'm going to come back here. My cat just came in the room with me. Hopefully she's not going to make an appearance. All right, 3.41 inches, and I have 2 increments. Okay, so I'm going to do 3.41 and 2 increments. Let me just check this other one to make sure. Yes, 5.89. Okay, all right. So there's my input dimensions. Then I have to specify that I have HCP, or again, the list of allowed reflections is the same. So I'm just going to leave this here. Hi, kitty. Yeah. Can you not try to get in my lap right now? It's going to be a little tough for me to work. Whoop. Okay. There you go. All right. So now the cat's in my lap. All right. So we'll just keep rolling with it here. Okay. Yes. Hi. I don't know if they can hear you purring or not. All right, so let me go ahead and run this and we'll see what we get here. Okay. Save. Okay. DP index. And there we go. Okay. So what do we got? Okay. So now if you remember back to the video on the cubic crystals, right? You remember that this is basically the same ratio we were getting for those patterns as well, right? Which makes sense. The arrangement of the spots is the same, okay? So if we look at, so we're getting out the G1 by G2 table. Now what I did here is I put in the code to actually truncate the table once it's mathematically impossible for any of the ratios to work. So the reason this stops after the third column is because none of these other ones are even in the ballpark, okay? They're all way too big. They're all way bigger than this, so I just truncated it there, okay? But we can see, right? So there's a hit right here. Let's see, is there a hit in this one? Yeah, so this one's pretty close. And yeah, this one's pretty close as well. So then I had it actually, it's automatically pulling them out here, okay, as to which ones could be the culprits, okay? So we have 3 possibilities here that could work, okay? So right off the bat, right, we can get rid of this guy in the middle, okay? The reason for that is we have non-zero L, non-zero L, okay? Mathematically, not possible for these ever to dot to 0, even though the ratio is close. So we can get rid of that guy immediately, okay, to make our lives easier, okay? So that one mathematically cannot work, okay? So now we can look at this guy here as well, okay? So 0, 1, 1, and 0, 2, 0, okay? So let's go back here to this, okay? So I put a little space here to do some working, right? So this is the equation here for the dot products, okay? Okay, so we have 0, 1, 1, and 0, 2, 0, okay? So let's just assign it to be 0, 1, 1, okay? And so then what we have to do now is we have to figure out indices that we can assign to G2 such that we get a 0 dot product, okay? Now notice, right, with this, I can't, for instance, make this 1, 1, 0. It has to be 0, 1, 1, or I could have used 1, 0, 1, okay? But again, because, right, it's hexagonal, okay, I couldn't use 1, 1, 0 here. It has to be 0, 1, 1. Oh, I'm sorry. My iPod is barking at me here. Oh, I'm sorry. Well, let's see if it stops because the cat's nice and comfy in my lap. And Lord knows you don't want to disturb a cat when she's sitting in your lap, right? Everyone knows that. All right. So let's just go with this here. Okay. So we're going to now input in here. Let's see. Now we know for the second one, though, right, that the third index has to be 0, okay? So what we can do right off the bat here is we can get rid of this term, right, because we know L2 has to be 0, so this cancels out, okay? So now, because H1 is 0, that goes away, and that goes away, okay? So what we're left with here, if we do the math, let me copy and paste this. Okay, so this gets removed. Oops. Okay. This gets removed. This gets removed. This gets removed. Okay, so we can get rid of that. Obviously, we don't need the 3 there. Okay, so this is what we're left with, okay? So now we know that K1 is equal to 1, Okay, so we can substitute that in here. Oops, come on. Equation editor, I hate you. Come on. Ugh. What's going on here? Okay, 4. All right. So we have basically, this is what we're left with, okay? Let me pull this over now. Okay. All right, and then we can reduce this down. Okay, so this is the final result here. Okay, so this is our constraint. Our constraint says that 2 times K2, actually let's move the minus over here, just so we put everything on one side, okay? So our relationship says that the first index has to be equal to, no, let's leave it this way. I don't want to use fractions. Okay, so this tells us that our first index has to be equal to 2 times the opposite of the second index, okay? But at the same time, we know that this has to be in the 0 to 0 family, okay? So let's think about this, right? Okay, I have to have, my answer has to be 0 to 0, okay? So my second index now has to be equal, I'm sorry, my first index has to be equal to twice the second and then take the opposite, okay? So is it mathematically possible to do that and still have this family, okay? Because what it's telling me is I've got to have a 0 in one of the first two indices and then a 2 or a -2 as the other one, okay? So if I put, say, -2 here, right, as the, or sorry, if I put 2 here as the H, okay, or sorry, if I put 2 here as the K, as the K2, then what it's telling me is my H2 has to be 4 bar, okay? Well, that's not going to work, right? Because then I'm not in this family, okay? Alternatively, if I stipulate that K2 is 0, well, then H2 has to be 0. Well, then that tells me that the family has to be 000, but it can't be 000. It has to be in this family, okay? So the end result here is that we can't mathematically get this to work, okay, and keep the stipulation that G2 is in this family, okay? So now this is trickier to do, okay? This is trickier to do than what we were doing with the cubic lattices, no question about it, okay? This is what we have to do, though, with the hexagonal lattice, okay? But this is how we have to eliminate possibilities, okay? So we can eliminate this as a result, okay? So that leaves this guy right here, okay? So let me go ahead and let me move this back and this back and this back. Okay, so we have 0, 1, 0 and 1, 1, 0 as the two families, okay? So for purposes of simplicity, let's make G1 be 1, 0, 0, because that will be equivalent, okay? So we'll make this be 1, 0, 0, okay? So then we'll go ahead and plug in for the rest of this. Now we know in both cases the L indices are 0, okay? So that means this term cancels out, okay? So now we need to, right, and that's 1, 1, 0. Okay, so now we need to plug in these here, okay? So basically everywhere that I see K1, that's going to get canceled out, okay? So that's going to get canceled out, and that's going to get canceled out, okay? So we're going to do basically a similar thing that we just did. here. So we're going to copy the, whoops. We're going to take this. We're going to copy it. Okay. So we're going to remove this term. We're going to remove this term. We're going to remove this term. And of course, we're going to do the same thing we did before. We're just going to get rid of that. Okay. And then H1 is 1. So therefore, you can substitute that in. And we end up with this. Okay. So now we end up with that out. -1. Okay. And then let's simplify this again. So we're going to divide through by -2. So we end up with -2 here. Let's get rid of the parentheses just to clean this up a little. Okay. Okay, so this is our constraint now. Okay. Our constraint is that K2 has to be equal to twice the opposite of H2. Okay. And we still have to be in the 1, 1, 0 family. Okay. So you might be looking at this going, well, how is that possible? Right? So, if I let, say, the H2 index be 1, okay, then what that's telling me is that K2 has to be 2 bar. Okay. So then I end up with 1, 2 bar, 0. And you might be thinking, well, that's not in this family. But now here's where you have to remember, right, the 4 index notation. If I come back here, okay, and I find the family, this is the family right here. If I expand this to 4 index notation, I get this. Okay, so let me come back here to this slide. Okay, and let me rewrite this. I should have probably put this at the beginning. 1, 1, 2 bar, 0. Okay, put the bar in there. Okay, so then if I have 1, 2 bar, 0, okay, if I convert that into 4 index notation, what I end up getting is, okay, so let me put it here. 1, 2 bar, 0. I end up with 1, 2 bar, 1, 0. And that now works. Okay, so that is in the family. This is why you need the 4 index notation. Okay, so now if I convert G1 to 4 index notation as well, okay, I end up with 1, 0, 1 bar, 0. Oops, sorry. I end up with 1, 0, 1 bar, 0. Okay, so there's my answer. Okay, and we mathematically prove that it works. Okay, because it's consistent, right, with the ratio, and the math also works. Okay, so that's our solution. Okay, that's our solution for doing this. Okay, so let me see here if I can get my, there's my zoom controls back. Let me hide these again for a second. Okay, so let me come back now to our actual pattern here. Okay, so again, this is G1, this is G2. Okay, so I'm going to insert now a text box. Okay, and G1 is 1, 0, 1 bar, 0. Let me clean this up a little. Arial. Let's make this way smaller. I think I had to make this like, yeah, we can make it bigger on this because the spots are spaced out a little more. On some of the other ones, we're going to have to be a little bit more conservative. All right, let's do 14. Okay. All right, that's good. come on, Control B. There we go. Okay, this is 1, 2 bar, 1, 0. Let me get these hideous arrows out of the way for the moment. And that's quadruple 0. Okay, so now the zone axis. Okay, I have to cross G1 with G2 and I get the zone axis, right? Now remember, I have to do 3 index notation for this. Okay, so this would be 1, 0, 0 cross 1, 2 bar 0. Okay, so I'm going to go to MATLAB just to do this quickly. And I have here DP zone axis. Okay, so my G, yep, 1, 0, and then I have 1, 2 bar 0. Okay, and let's see here. DP zone axis. Okay, so based on how we assigned the spots, it's telling us the zone axis is 0, 0, 1. You can easily convert that to 4 index, and that would be 0, 0, 1 bar. Okay, so our answer here is 0, 0, 1 bar. Okay, so unfortunately, we guessed wrong to give us 0, 0, 1. So if we wanted to adjust this, we'd have to go ahead and reassign some spot indices here, okay? But let's just go with the assumption that we're leaving this here, okay? So now vector math to solve some of the rest of these spots, okay? So this is just like how you would do normal vector math, except now you're adding 4 components, okay? So if we do this guy right here, I'm adding G1 to G2, okay? So what do I get? I get 2 bar 0, 0. And then this spot is simply half of that. So I get 1 bar 0, 0. And then now these are opposites. Two bar 2, 0. And now this is the opposite of this. -1, 2, -1. This is the sum of these two. So I end up with 0, 2, 2 bar 0. This is half of this guy. 0, 1, 1 bar 0. And now based on the rest of this, I'm just taking opposites, right? So -1, 1, 0. Zero, 2 bar, 2, 0. We'll do just a couple more of these. This is 1 bar, 0, 1, 0. Okay. Now notice, okay, all 6 of these closest spots, okay, these are all equidistant. They should be the same family, and they are. Okay, these are all in the 0, 1, 1 bar 0 family. Okay, this is why we use the 4 index notation, because we can see that. Okay, the next closest spots, right? These, okay, right here, here, and here. These are all in the 1, 1, 0 or 1, 1, 2 bar 0 family. Okay, so if we now again, if we wanted to do this, okay, we can add this vector to this vector to give us this as well. Okay, so what do we have there? We have 1, 1, 2 bar 0. Okay, right there. Okay, and then so on and so forth, right? If we want to solve the rest of these, okay? So what I'm going to do here, let me make a copy of this, and then put it underneath here, okay? So now, what do we do here if we want to apply the soft rules, okay? Let me get rid of, whoops, everything but my original two, okay? So if we want to change this, okay? There's a really quick way to do this, okay? So we could talk about reassigning indices and doing this, but really the really simple way to do this, okay? Because all I have to do is swap a negative, right? All I have to do, make this negative, and then I have to make one of these two indices, I have to make it the opposite, okay? That's all I have to do, okay? So if I switch this guy to 1 bar, oops, 1 bar 0 1 0, then I'm set, okay? Okay, so now we can prove this just to satisfy our curiosity, okay? So we're doing 1 bar 0 0 cross 1 2 bar 0. Okay, let me go back to MATLAB. So we have 1 bar 0 0 cross the other one, and we should get out, yes, so we get out 0 0 1, okay? So if all you have to do is flip a negative, that's the quickest way to do it, okay? You don't have to kill yourself with that one, okay? That's an easy one. That's a quick fix, okay? So, you know, just for the sake of argument here, right, we can do a few of these, okay? Or actually, you know what? I'm not even going to do that because that's pretty easy, right? But that's how you would reassign this if all we have to do is do a negative, okay? So this is definitely one of the quintessential zone axes when you're dealing with hexagonal lattices here, okay? So we're going to kick it up a little bit here and go on to the next one, okay? One of what I call the big three in terms of the hexagonal lattices, okay? And that's this guy right here, okay? So let me go ahead and grab these lovely arrows again. Okay, so point symmetry, right? This is 2 mm point symmetry, okay? Very obviously, right? So we'll put 2 mm here. Okay, and again, this is what the vast majority of the patterns in the DPs have, is they have this kind of symmetry, okay? So G1, G2, right? Very obvious, okay? Again, I have, looks like 6 gradations here for my G1. Oops. It's not letting me. Do I have something like, oops, do I have this on? No, I don't. Okay, I don't know what that's. I'm trying to get this to constrain to be. I want it to stay flat. I guess it's there. Okay, there we go. All right. Now this pattern, of course, is probably not perfectly level in terms of the spots. I think yeah, so it's rotated just a little bit here, it looks like. So what I can do actually to alleviate that really quickly is I can just rotate this very slightly. More rotation options. Rotation. Is that 1 degree? Or is that too much? Well, let me do half a degree. No, it won't. Okay. All right. We'll just have to go with it here. Yeah, so this is unfortunately not perfectly flat, but we'll go with it anyway. So the other option, if we wanted to be, you know, super sticklers here. So this is claiming that, oh, it's claiming that it is. So, okay. So we have 5.09 over 6 gradations. So we'll go back to MATLAB here. And we'll go to, oops, DP index. 5.09, 6 gradations. Okay, and we'll go to this guy. So now we have 4 here. Cat is still in my lap. So hopefully that's good news. Okay, come on. Where are you? I'm hoping I don't run out of battery here. I shouldn't. Is that close? Oops, oh, mouse is on the floor. Sorry, let me grab that. Okay. Yeah, so this is clearly a little bit off here, so we'll just have to make do. Okay, whoops. Okay, so what do we have here? Okay, so it's not even, yeah, so 5.64, and that's 4 gradations. Okay, 5.64, 4 gradations, right? So let's go ahead and run it again. So I'm going to do DP index. Okay, so we get 2 hits. Okay, so measured ratio is about 0.6. And so we get 2 hits here. So one, now again, right? Look at this one, okay? Non-zero L, non-zero L, okay? Mathematically, can't get those to work, okay? Can't get those to work. So by deductive reasoning, this has got to be it here, okay? And now this is an easy one, okay? Because my first set of indices is only non-zero with the L, and my second set is 0 for the L, okay? So it's very easy to go back here now to this guy, right? And very easy to show that the dot products are going to be 0, okay? So again, let's assume here. Now again, I have to do 0, 0, 2 here. I can't do 2, 0, 0 or 0, 2, 0, okay? So let's let HKL2, so we know that it has to be in this, is that right? Yes, in this family, okay? Which again, if I expand to 4 index notation is this, okay? So all we got to do is plug and chug, okay? So if we plug and chug, right, it's very obvious this term's going to be 0. And since my H and my K here are, for G1 are both 0, then this term is also going to be 0, okay? So everything goes to 0. And so I already have, I could basically use any G vector I want in this family, and I'm going to get a 0 dot product with this, okay? Perfect, right? So why don't we go ahead then, and for the sake of simplicity, let's go ahead and just use 1, 1, 2 bar 0, okay? So again, we go back to the slide here, and let me copy some stuff here. Okay, get these out of the way. Okay, 0002, 1, 2 bar 0 right there. Now I need the zone axis, okay? So I'm doing 002 cross 110, okay? We'll come back to my MATLAB script. And we have 002, 110. Okay. Run this and we get out 1 bar 1 0. Okay. Now we have to convert this to a direction. Okay. We have to use the formulas here to do this. Okay. So right. So we have to come back here. And so if I have a piece of paper here. Where'd my pen go? Where'd my pen go? I thought I had a pen with me. I know the answer, but I'm just trying to, I want to do this correctly here. So what happened to my pen? It's going to be hard to write with. All right, let's see if we can just do this mentally here. Okay. All right. So we have 1/3 times 2u minus v. Okay. So that's going to give us, let's see, minus 1/3, right? And then if we do the same, that's going to give us minus 1/3 for the first index. If we do the same thing for the second index, we're going to get 2 minus 1. So that would give me, wait, that doesn't make sense. Okay, no, sorry, let me backtrack. Okay. Okay, first index, I have 1/3 times 2 times minus 1 minus 1. So that's going to give me 1/3 times minus 3 is minus 1. Okay, if I do the same thing for the second index, I'm going to end up with 1/3 times 2 times 1 minus 1. So I end up with 1/3 of 3. So I end up with 1. Okay, then my third index, because it's the sum of the opposites, is 0, and then the last index is 0. Okay, so this becomes 1 bar 1 0 0 for my zone axis. Okay, all right, so I end up with 1 bar 1 0 0 for the zone axis. All right, and so just like we did before, right, we're going to go ahead and solve a few of these spots. So we're going to add these together. 1 1 2 bar 2. That's 0 0 2. That's obviously 0 0 4. And that's obviously, oh, sorry, 0 0 4 bar, 0 0 4. Oops. Let me do this to make this easier. This is the opposite. So that's 1 bar 1 0. Okay. That's 1 bar 2 2. That's the opposite. All right. And then let's do one more right here. And we get 1 bar 2 2 bar. Okay. Now, one thing, I didn't do this in the last pattern. I should have. But again, right, the Weiss zone axis law, I should get a 0 dot product between this and all of these if I did this correctly. Okay. So just, inspecting, right? This appears, this does look valid, right? These are obviously all good right here. Okay. These two are also good. Right? Because you have zeros here, and then you have the 1 and the 1 bar and the 1. And then, yes, everything else is the same, right? So again, you should get, these are all spots in the 0 order Laue zone. So you should get a 0 dot product between B and G, okay, for all of these, okay? Again, as we see, right, these spots are all equidistant. They're all in the same family, okay? The 1 1 2 bar 2 family, okay? Again, right, constraint is third index has to be equal to opposite of the sum of the first two, okay? All right, so let me go ahead and copy this and paste it. And now let's talk about if we want to do some reassigning of the indices. So now if I wanted to change the zone axis from 1 bar 1 0 to 1 bar, or sorry, to 0 1 1 bar 0. Okay, now I can't get rid of the negative. Negative has to be there. Okay, that's the constraint, right? Is with the third index there. Okay. If I want to do that, right? Okay, I'm going to have to then reassign some of the indices. Okay, so I know for a fact, right, that if I reassign these, that these spots are all unaffected, okay, right? These all still dot to 0. The problems are all these other ones, okay? So let me go ahead and delete these, right? So basically, we stipulated this was G1 and G2. We have to figure out now what we're going to reassign for G2, okay? So we know this is the zone axis. That's the out of page direction, okay? If we figure out the lattice direction parallel to G1 and we do B cross that direction, we're going to get a G vector that points toward G2, okay? That's the property, one of the properties of the real space, reciprocal space lattice relationship, okay? So what lattice vector is parallel to 0002G vector? Well, it's very obvious, right? That's 0002 lattice vector, or just 002 lattice vector, okay? So then what we have to do is we have to convert this into 3-index notation, okay? Unfortunately, it's not as simple as just dropping the third index, okay? All right, so what do we have to do here? So we have to do, so for the first index, we have to do u prime minus t prime, so we end up with -1, and then we end up with, for the second index, we get b prime minus t prime. So we end up with 1 minus -1. So we end up with 2. Okay. So we end up then with 1, 2 bar 0 as the direction. Okay. So let me just put this here in 3-index just so we have it safe for us. 1, 2 bar 0. Okay, let me make sure, just quickly sanity check here, that makes sense. So we have, yeah, that works out. We end up with the 2 there. 2 times, yeah, so that works, okay? So yes, so 0, 1, 1 bar 0 is actually 1, 2 bar 0 in 3-index notation, okay? So if we do 1, 2 bar 0 cross 002, we're going to get this G vector, okay? So again, right, we can do that cross product, okay? I have another program here to do this, okay? So the zone axis is 1, 2 bar 0, okay? And then, yes, that lattice direction is 002, okay? So we can save this dp g2 solve. Okay, so it's telling us that our answer is 4 bar, 2 bar, 0. Now we have to reduce this down, okay? We have to reduce this down to an appropriate set of indices, okay? So if we do that, we know that the family has to be, right, this family right here, okay? Although I think I did something, did I do something amiss here? Because it shouldn't be, no, see, something's not right here. 0, 1, 1 bar 0. I shouldn't be getting a negative here. Did I put, oh, okay, my bad. Let me redo this again. Okay, so we drop this here. Okay, that's positive. Okay, so no, it should be my bad. Okay, so this should be positive. It should be 1, 2, 0. Okay, let me try it again. Okay, there we go. Okay, so 4, 2 bar 0, so that reduces down to 2, 1 bar 0 to make sure it's in the same family, and then 2, 1 bar 0 becomes 2, 1 bar, 1 bar 0. Okay, so this spot up here, whoops, going on here? Come on, what are you doing? Okay, so this spot here becomes 2, 1 bar, 1 bar. Yes, 2, 1 bar, 1 bar, 0. Okay. This then reduces down. 2 bar, 1, 1, 0. Okay, do the vector math. Okay, that's a 2 bar there. Oops. -1, -1, -2. And then we'll do one more over here. That just becomes a 2 for the last index. All right, does the vector math work? Okay, I should get a dot product between B and all of these indices here. Okay, so yes, looks like we're good to go. Okay, all right. So those of you familiar with the hexagonal lattice, you'll recognize this. This is what's called M-plane, right? So planes that are of or directions that are of this form here, the 0, 1, 1 bar 0 family. Okay. In the case of what we did before here, right, this would be C-plane, okay, because we have 00001 here. Okay, so moving along here. All right, we'll move on to the next one here. Okay, so let me grab my arrows here. Okay, point symmetry. Yes, this is 2 mm. So now this is a unique structure here because we now see some holes, right? We see some holes where we think we might, be seeing spots, but we don't. Okay, so G1 and G2. It's not very obvious, but this is actually the shorter of these. Okay, the ones pointing up and down. Okay, so let me go ahead here. Okay, that's close enough. Okay, and then we have 6 gradations there. Okay, so we can actually see that's 5.16. Come on. 5.16, and that's 5.3. Yeah, so that is a little bit longer. Okay, all right. So we have 5.16 over 6 intervals. DP index. And we have 5.37 again over 6 intervals. Okay, but now we have, 6 intervals here. Okay. All right. So let's go ahead and run this. DP index. Ooh, that's interesting. So it's giving me a non-answer. Cutoff is okay. So it couldn't do it. That's real interesting. Let me take a look here. Let me just generate here's G1 by G2. We might have to do this. Okay, so there's my measured ratio. Okay. Yeah, see, this is really close to 1. So that's part of the problem here. What I might need to do is make my tolerance a little bit tighter. Okay, so let me try this. So what I have here is, in this code, is I have a cushion. Okay, so I have 90. Yeah, so that's part of the problem, is I have a cushion here. All right, so let me make the cushion a little bit tighter here. And let's do 98 and let's see if that works. If not, we'll just have to manually look at the table. Okay, so now it's giving us a bunch of possibilities here. Again, part of that is, right, so this is very close to 1, and all of those diagonal terms, right, in the G1 by G2 table are all going to be 1, okay? So that's part of why you're seeing that, okay? Let me see if I make this 99, if that helps us any more. May not, but no, it doesn't. It's basically giving us all of the diagonal terms. Let me see here if I go a little bit the other way. No, so it's not doing that either. What about if I do 97? Okay, so yeah, it's still doing that. All right, so let me pull up the whole table. So I did program this in here to give me the whole table. All right, so where is it? Okay, G1 by G2 pred full. Oops, sorry, kitty. Oh, there's my pen. You were sitting on it. Okay, of course. Right, let me pull this up here. Okay, so here's the table right here. Okay. So we've got yeah, so a bunch of hits here. Let me see if I can't tighten this up even more. So my ratio, what did it give me? Gave me ratio, yeah, 0.96. So why is it not? I'm curious as to why it's not doing that. This, of course, so really it shouldn't be going past this this first two, right? This is really only where it should be going. Okay. So why is it? Well, no, it's not technically true. It could be okay. So we have these other ones here. So yeah, so this one we're gonna have to put our thinking caps on here a little bit more. Okay. Let me try if I just really make this tighter here. Let me see if it, no, it's still doing the same thing. Okay. All right. No big deal. Okay. So we have, let's just take a look at some of these here. Okay. So again, one of the constraints, right? One of the constraints is that we have to have the spots arrangement to work out, right? And if we don't, then then that would be an indication that the solution probably is not valid. Okay, so if we come back here, so basically the very first solution is this guy. Okay, so it's telling me G1 is this family and G2 is this family. Okay, so very obviously I can look at that and I can see that that is correct, right? In terms of a zero dot product. Okay, let me pull up the full table here again. Okay, so there's the full table, right? So if I look now here, okay, that would correspond to this entry right here. Okay, so that is very, very close to where I was expecting it. So we have measured, oh, I know why. Okay, as long as we find measured values greater than that. Okay, so that's why it's going to do that, because that ratio is, yeah, okay, so it's always going to be there. So yeah, so that would explain why it's always finding it, because you're very close to 1 with the ratio. Okay, so yes, so this is the hit right here, right? So find measured greater than the cushion. Okay, yeah, I might need to rework something with this to to see if I can do the cutoff a little bit better. But anyways, yeah. So here's what we have here with the table. Okay. So this is telling us that G1 would be the first G vector and G2 would be the second. Okay. So if we look here, right, that mathematically can certainly work. This one can't, right? Because we have non-zero L, non-zero L. Okay. If we go through some of these other ones, these can all be eliminated because those again are non-zero L and non-zero L. Okay. Some of these I think are mathematically multiples of the other. So like this one here is just a multiple of this guy. Okay. So we can get rid of that. So really what we're left with then is a few different answers here that could work. I know that the answer is this one specifically though, okay? So then if we wanted to go through here just to satisfy our curiosity, okay? So again, I know that the answer is this guy, okay? And actually, you know what? I need to really quickly go and get my charger because this took a little longer than I thought. So let me put the mic down for just a second here. Let me go grab that so we don't lose everything. All right. All right. Then mic will not fly out of my seat here. Okay. I think we're good to go here. All right. We got juice. So gonna take more than a dead battery to stop us, huh? Okay. So again, I know this is the answer, okay? But and we know we eliminated some of these, okay? So if we want to show, right, why this guy can't work, okay? So let's go ahead and just do that. And then we can use similar logic for the other ones. But I'm just going to go through that one as an example, okay? Excuse me. All right. So we'll let G1 be 0, 1, 3. Okay, so let me come back here. Okay, so we'll let G1 be 0, 1, 3. And we know that the second has to be, okay, 0, 2, 0. That has to be of the family 0, 2, 2 bar 0. Okay, so we have to have a 0 index here. So this guy again, bye-bye. Okay, every place I see an H1, that's going to be 0 as well. So that term's going to be 0, and that term's going to be 0. Okay, so we'll go ahead and copy this. And you can probably see where I'm going with this. This is very similar to what we did in the first example. Okay, so that's going to get removed. That's going to get removed. That's going to get removed. Whoops. No, I don't want to type equation here. Okay. Oops, let me cut this out. Okay. Okay. So then we're stipulating that K1 is 1. So we can, whoops, come on. I hate you, equation editor. Okay. Get rid of the plus. Okay. Let me get rid of, let me just copy this so we know that it's there. Okay. So what do we end up with? We end up with something very similar to what we've already seen. Okay. Which is that we have minus 2K2 equals H2. Okay. So we have, now again, here's our family. Okay. Our family has to be in this family. Okay. But the stipulation again is that the first index has to be equal to twice the opposite of the second. Okay. So again, mathematically, there's no way for that to work and still get this. Okay. The only way this could work is if both of those are 0. Okay. But that can't happen, right? Because, okay, it's constrained that you have to have at least one of those be a 2 and the other be a 0. Okay. So again, mathematically, that combination, even though the ratio is close, right, is reasonable, it doesn't work. Okay. The math doesn't work. We can't assign indices to it. Okay. And you can do the same thing for the rest of these that were also mathematically possible. Like these two right here, we could do the same thing. Okay. And again, this one, this is just a linear multiple of the first. Okay. So let's go back now and let's look at this guy, which I know is the solution. Okay. All right. So we're going to let G1, let's be 0, 1, 0. Okay. And then the other one is going to be 0, 2, 0, otherwise known as 0, 0, 2. Okay. And yeah, so, this is very straightforward here. Okay. In terms of, right, so we could basically use we could use 0002 or 0002 bar. We're going to get a 0 dot product. Okay. Nice and easy with this. No question at all. Okay. So for the sake of making this easy, let's just do 0002 to make the math nice and convenient. So we're using less negatives. Okay. So when we come back here, right, and I need some okay. So that's 0002. And this, okay? So 0, 1, 0, we have to convert to 4 index. So that's 0, 1, 1 bar, 0. Okay? And then it's just a matter, right, of, doing now I'm going to copy some of these here because this is actually, these are all the same here. Okay? Just to make this a little quicker. Now, this was one of the ones, I remember this now. This is one of the ones where I had to reduce the font size down. Okay, so let me come back here. I remember I had to make this 10 in order for this to work. Yeah, that should work okay. You can see some of these spots, they just get really tight here with the spacing. Okay, so, right here, add this to this, okay? So we have 0, 1, 1 bar, 2. Do the opposite. 0, 1 bar, 1, 2 bar. Oops, and I'm sorry, we didn't Didn't do the zone axis. All right, let's do the zone axis here. Okay, so we got to do 0, 1, 0 cross 0, 0, 2 to get our answer. Okay, so let me come back here. 0, 1, 0 cross 0, 0, 2. So we get dp zone axis. Okay, and we get 1, 0, 0. Okay, so we have to convert 1, 0, 0 to a crystallographic direction. Okay, so 1/3 times quantity 2 times 1 minus 0. So that gives us 2/3. Okay, for the second index, we're going to get minus 1/3. For the middle index, we're going to get opposite of the sum of those two. So we'll get minus 1/3, and then the last will be 0. So then we have to multiply through by 3. So our answer here is 2 minus 1 minus 1, or 2, 1 bar, 1 bar, 0. Okay, that's our zone axis. Okay, does it work out with the math? Yes. Okay, math works. Okay, all right, so let's go ahead here. We'll do some more of these spots. Yep, okay. Put this one back. So now this zone axis, while I'm doing this, okay, this is probably the most important zone axis that is studied in crystals with hexagonal unit cells. Okay, again, I say crystals with hexagonal unit cells because not all crystals with hexagonal unit cells are technically hexagonal crystals, okay? But this is probably, especially with HCP and wurtzite, this is probably the most important zone axis, the most technologically relevant zone axis. This is the equivalent of 110 for diamond cubic, okay? So this is another one of those really, really important zone axes. All right, so now, how about some of these other ones right here? Okay, so this one, we have to imagine, right, if we had 0, 0, 1, we'd have to add that to this, okay? So what do we get here? We get 0, 1, 1 bar, 1, okay? Oops. I didn't make the spacing, whoops. Didn't make the spacing too long. Okay, so that's 0, 1 bar, 1, 0, 1, 1 bar, 1 bar. Okay, you can see, yeah, this gets a little tight in here. All right, we'll do a few more of these. Okay, so what do we have here? We have, oops, let me just start with this one. Okay, so that's going to be -1 right there. And then on the other side, it's going to be +1. Okay, so I apologize. I know that's getting a little tight in here, but yeah, that's what happens with these. Okay, so that's the solution. Okay, now you'll notice also I have these holes here. Okay, just like what you have with the diamond cubic system, you can get double diffraction, and you can see these kinematically forbidden spots in here. Okay, if I take this, here, let me copy this and paste it. Okay, so if I remove all these, okay, control, transparency. Okay, so now if I get strong diffraction from, say, this spot right here, that's a 0, 1, 1 bar, 1 family. Okay, I transpose the pattern over by that amount. And what do I get, right? I get these spots filled, okay, where there used to be none. And then I can now see spots that are kinematically forbidden. Okay, the 000 L family, where L is not even. Okay, where L is an odd number. Okay, I can also see it, right, if I have this spot also serving as my incident beam. Okay, so there's more than one way to, skin the cat. Although maybe I shouldn't say that because my cat's still sitting behind me on the chair. Okay, so yes, just another little segue here. Talk about double diffraction here. Okay, but yeah, this is commonly observed again with this zone axis pattern. So okay, now if we want to talk about re-indexing this, okay, so what we would want to do here, we would reassign this if we wanted to apply soft rules. This would be 1 1 2 bar 0. Again, we can't get rid of the bar, right? We can't get rid of the bar. It's got to be there. You have to have this constraint here. Okay, let's copy those. Okay, so my 0002 is fine. Okay, nothing wrong with that. That still gives me a 0 dot product. What I've got to worry about is, sorry, this was my G1 here. Okay, what I have to worry about is this one. Okay, so now if I do G2 cross B, I end up with this direction. Okay, so now what's the lattice direction corresponding to 0002? Well, very obvious, right? That's 002 or 0002. Okay, so now I have to convert this guy to a 3-index notation. This is actually an easy one. The answer is 1 1 0. Okay, so basically, right, I have 1 minus 2 is 3, and then I have 1 minus 2 is 3, and then 0. So I have 3 3 0, which reduces down to 1 1 0 in 3-index notation. Okay, so then if I do 002 cross 1 1 0, I'm going to get the answer that points in this direction. Okay, so we'll come back here. Now I have to actually rearrange this because I'm not doing B cross V1, I'm doing V2 cross B. So this is going to be the first one. So that's 0, 0, 2, and this is 1, 1, 0. Okay, so that should, yes, so that should work. Okay, so let me go ahead here. dp g2 solve. Okay, so it's giving us out the answer as 2 bar 2 0, which has to reduce down. Okay, so we reduce 2 bar 2 0 down to 1 bar 1 0 because we know that it has to be in this family right here. Okay, has to be in the 1 bar 0 family. Okay, and again, right, if we just look at 1 bar 1 0, it's not obvious. We have to use 4-index notation. Okay, so the answer here, 1 bar, sorry, I'll get it right, 1 bar 1 0 0. Okay, all right, so there's my answer, and we can solve a few of these spots. There's a 2 there. I'll just do these closest ones here. This is where the bars are helpful because they're a little more compact. But yeah, you're nuts if you think I'm going to draw all those bars on there. I mean, ooh, take a long time to do that. Okay, 1 there. It's raining outside. I don't know if you can hear that through the mic or not. Okay, and then we'll do these last remaining 4 spots here. Assuming we've got the room, So that's going to be a -1. And that's going to be a 1 instead. That's going to be a 1. And that's going to get put to a -1. Okay? All right. So there it is, re-indexed with the soft rules. Okay? This is a plane. This family is what's called a plane. Okay? Anything that's in this 1, 1, 2 bar 0 family. Okay? So those are kind of your three main. There's other ones too. There's R plane. That's another one. But again, in my opinion, this is probably the most technologically relevant zone axis for HCP and wurtzite. Okay? Okay. So I got one more example, and this is probably, I know this is the most involved one. Okay? So we've done the big three to this point. We're going to do one more here, and this is the trickier one. Okay? So we got this guy. Okay? It has the same point symmetry, the 2 mm. Okay, and we have these, open holes again, which is indicative that we probably have some systematic absences again, or spots that we might see via double diffraction. Okay, so again, here's our G1 and our G2. Okay, just like we would expect, right? So let's go ahead here. Copy, paste. Okay. Okay. So G1, we've got 5.3 and 6 intervals. DP index. Oops, 5.3, 6 intervals. Okay, this guy, we only have 2 intervals. Although, actually, if we wanted to, okay, we could measure like this and get 3. Okay, so why don't we do that? Just to, help us out a little bit here. Okay, so that's 5.34 over 3. Okay, all right. So let me delete these now, since we don't need them anymore. And let's run the script. So we've got DP index. Oops, and let me put my cushion back down to where it was. Okay. Okay. So we get a bunch of different hits here. Again, let's look at ones we can pitch. Okay. This guy we can pitch. Okay. L's are the same. In fact, this is just a linear multiple of this. Okay. This is also just a linear multiple of this. And this is not a linear multiple of this, but the two L's are both non-zero. Okay. So those can both be pitched. All right. So that leaves us with 3 here. Okay. This is also a linear multiple of this. Okay. So that can't work either, right? So again, linear multiple would imply, right? So let's just say that this was the solution, okay? We would be seeing another spot here, okay? Because this is twice the length of this, right? What it's basically saying is we've got a ratio that's equal to 0.5. Yeah, so very, very close to 0.5, okay? Okay, so this can't work, right? Because let's say that this is 0, 1, 0, and 0, 2, 0. Okay, we would be seeing, right, a 0, 1, 0 spot here if that was the case. Okay, since we're not seeing the spot there, it can't work. Okay, so we can rule that out. Okay, so we're left with 2 possible answers here. Okay, so we're left with 0, 1, 0 and 1, 1, 2 and 0, 1, 0 and 0, 2, 1. Okay. So I honestly don't know which of these it is. I know what the zone axis is. Okay. So what we're going to have to start with here is, I think, the same thing we did before. We're going to have to start by seeing if we can get the math to work. Okay. So let's go ahead and let's try this first one, okay? So we're going to start with 0, 1, 0 for G1 and 1, 1, 2 for G2. Okay, so let me go ahead here. So we'll call this 0, 1, 0 for G1. Sorry, and that's 1, 1, 2. Okay, 1, 1, 2, which is the same as 1, 1, 2 bar 2 family. All right, so now we're assuming that G1 is that, okay? So now once again, because we have 0 index there, this guy gets canceled out. Anywhere we have H1, that also gets canceled out. Okay, so we've got that canceled and we've got that canceled. And we're gonna copy that right there. And let's simplify some of this. Okay, so we're gonna simplify that. And we're gonna simplify that. Right, and let's get this out of there. Okay, so we're left with this. And then we can rearrange this just like we've done here. Whoops. Okay, so we know K1 is 1, so we can make the substitution. And if this thing will let me. Yeah. Okay. And oops, did I copy the wrong thing? I did. All right, sorry, let me go back here. My mistake. Okay. Let me do this again. Okay, this one should be gone. There we go. So K1 is non-zero. X. Okay, then we can make the substitution for K1. Since we're assuming that's 1, put 4 in there. And we're ending up with, oops, come on. Get that out of there. Okay. So that simplifies down. Okay, minus sign. Let me move this out of the way. And then let's simplify this some more. So we have minus 2. Okay, so we end up with a similar stipulation here that we've seen. Okay, so we have the stipulation that H2 must equal 2 times the opposite of K2. All right, so now the question is, can this work? Okay, so at first glance, you might think no. Okay, you might think that's not possible, but again, you have to remember the 4 index notation here. Okay, so this actually can work. Okay, so if, for instance, whoops, let me leave this here. Okay, so again, the stipulation is H2 is twice the opposite of K2. So let's say, for instance, I make K2 1, then H2 has to be minus 2. So what does that give me for I? Well, I take opposite of the sum of those. I end up with 1. Okay, and then I have 2. So this is inside of the family. Okay, so mathematically, this works. Okay, this is a viable solution. So this could be the solution. What we need to do, though, now is, because we have that other hit in the table, we need to go ahead and see if we can't rule that out. Okay, so I'm going to copy this and paste it here. Okay, and we're going to do this again with the second solution, which is this one. Okay, so now we're talking about 0 to 1. And now my family here is 0 to 2 bar 1. okay? So just like we had, let me see, yeah, we'll delete these just to make this easier. Okay, so yes, third term goes away because I have a 0 index for G1 in the L position, and I get the same terms gone here as well, okay? So it looks like I end up with literally the same thing I had before, okay? So let me just, okay, so I end up back with this, okay? I end up with the stipulation that I have 2K, that I have H2 has to be equal to the opposite of two times the opposite of K2 and be in this family, okay? The only way for this to work though, okay, so let's think about this here. So if, for instance, if I let K2 be 0, okay, then that would require H2 to be 0. Well, that can't work, right? Because then I would end up with 2 0 indices, which I can't have, okay? So let's say then that I let K2 be 1. Well, that's not going to work either because then I have an index of 1, okay? So my first 3 indices have to be some combination of 0, 2, and 2 bar, okay? I can't have anything beside that, okay? So there's really no way for this to mathematically work either, okay? The only way this ends up working here is if I have 0 for this and 0 for this, but then I end up with 2 zeros, and I'm only supposed to have 1 0, okay? Same thing if I have 2 for K, if I have 2 for K2, then it's telling me my H2 should be 4 bar, right? Well, that's not going to work either because it's only supposed to be, I'm supposed to again have 0, 2, 2 bar, okay? So I shouldn't have twice one of the indices, okay? So there's really no way for this to work, okay? In order for this to work, I would have had to have opposite K2 equals H2, and I don't, okay? So we, again, mathematically can rule this guy out, okay? So this most likely is going to be our solution, okay? So let me go ahead and delete this panel so we don't end up causing an issue. Okay, so let me go back here and copy some text box as well. Okay, so here's my G1. So that's 0, 1, 1 bar 0. We're converting to 4 index notation, okay? And then, okay, we're going to use 2 bar 1, 1, 2 for my answer here, for my solution, I should say. Okay, so we have 2 bar 1. Okay. All right. We need a zone axis. Okay, so we're going to cross 0, 1, 0 with 2 bar 1, 2. Okay, and see what we get. Okay, let me go back. Just make sure here. Yep, that's right. Okay, so 0, 1, 0 with 2 bar 1, 2. All right. So 2 bar 1, 2. DP zone axis. Yes. Okay. So we get 1, 0, 1 for the zone axis. Okay. And now we need to convert that to 4 index notation. Okay. So 1/3 times 2 times 1 minus 0. So we end up with 2/3 for u. We end up with minus 1/3 for I should say u prime. We end up with minus 1/3 for v prime, we end up with minus a third for t prime because I'm taking opposite the sum of the first two, and we end up with 1 as the w prime. So then we have to multiply through everything by 3. Okay, so what we end up with is 2, 1 bar, 3. That is the zone axis. Okay, so we put this here. We get 2, 1 bar, 3. Okay, and then let's do the sanity check. Do we get a 0 dot product with these? Let's see. This one, obviously, we do. This one, we get, let me see here. We get 4. We get minus 1. Let me do this here. Okay, so we get minus 4, minus 5, minus 6 plus 6. Yep, so the math works. Okay, so there's our zone axis. Okay, and then so now, right, just like before, we can do a little vector math. Spots are spaced a little bit more generously here, so we can kind of navigate this a little bit easier. 0, 2, 0, yeah, like that. Okay, this is half of the spot, or half of the distance, I should say. Okay, then I'm just taking opposites here. Right, so you notice again, we have these very distinct openings here, right, where we don't see these. Okay, so we'll get to that in a second. Okay, so this guy right here, okay, some of this and this, so we end up with 2, 0, 2, 2. Now again, at first glance, you might think, okay, 6 mm, but it's not, okay? These are not all the same 60-degree angle, okay? This is actually 2 mm point symmetry. So, right, we showed it when we did the measurements that we weren't at that 0.577 like we were when we did the C-plane example at the beginning, okay? One bar, 1. Okay, 2 bar. Oh, sorry, 2, 0, 2 bar, 2 bar. Okay. And there's one more over here. We can take the opposite of. There we go. Okay. Let's see. So yeah, we're missing this spot right here. Okay, so this spot would be, if we did have it, it would be the sum of these two. Okay, so if we added these two together, we would have 1 bar, 1 bar, 2, 1. Okay, and that is not allowed. Let's see, let me do this again. No, that's not. Yes, so we're adding it together. 1 bar, 2, 1. Right, so yes, that's not in the allowed list of reflections. Okay, so yeah, that is consistent with what we would expect to see. You also notice, right, these two spots are not the same family as these 4. Okay, that's consistent with the point symmetry of the group here. Okay, same thing, right, when we see these guys. Okay, because this is of course just a linear multiple of this. Okay, so last thing, if we want to do it, okay, is if we want to apply soft rules, okay, let me copy this and paste it. Okay, so if we want to apply soft rules, okay, we're constrained to keeping the 3 here. We can't move that, okay? That has to be there. But what we can do is we can do 1, 1, 2 bar 3, okay? We can do that, okay? So let's delete all these other ones except G1 and G2. Okay, so just by inspection, right, we can just rearrange this guy to give us that, okay? And we're going to get a 0 dot product, okay? To make our lives easier, okay? So now we have to figure out how to reassign these indices, okay? First thing we got to do is figure out 3 index direction here for 1, 1, 2 bar 3, as well as 1, 1 bar, sorry, there isn't a bar 0 there, as well as 1, 1 bar, 0, 0, okay? So if we're doing this for, let's do this for this guy first, okay? So we have 1 minus 0. We have 1 bar minus 0. Okay, so this is very easy. This is just 1 bar 0 direction. Okay, so let me go back to this and just put this in here. Okay, so now as far as this guy is concerned, so we have 1 minus opposite of 2 is 3. We have 1 minus opposite of 2 is 3, and then we have 3. So we have 3, 3, 3, which is just 1, 1, 1. Okay, so we do 1, 1, 1, and then we're crossing B with this lattice direction, which we established in 3 index notation, would just be 1, 1 bar 1. Okay. Again, we have the parallelism, right, that this is the equivalent direction in 4 index notation. Okay. So go ahead and compute that. Okay. And so we get 1, 1, 2 bar. So that's actually already in the family. Okay. It's already in the family. So all we have to do, we don't have to multiply or anything. So we have 1, 1, 2 bar, 2. Well, 2 bar, I should say. All right, so let's do the math here, make sure everything dots to 0. So this clearly works. Does this work? We have 1 plus 1 is 2, plus 4 is 4, minus 6. Yes, so this works out. Okay, perfect. All right, so we'll do a few of these here, and then we will call it a day, or an early evening, I should say. So we have 1, no, so we have 2, 0, 2 bar, 2 bar. Sorry. 1, 0, 1 bar, 1 bar. Okay, do a sanity check here. Does that end up dotting to 0? We have 2 minus 2 minus 4 minus 6. Did I mess something up here? Let me see. I shouldn't have. 2. No, that's correct. Okay, now that works. Nope, everything's good. Okay, let me copy this. Flip all these. Okay, do a few more here. Okay, so that's going to be 0, 2, 2 bar 2. And that's going to be 0, 2 bar 2, 2. And that's going to be 0, 1 bar, 1, 1. Okay, and that's going to be the opposite. So I have 0, 1, 1 bar, 1 bar. All right, let me make sure I did that correctly. We added those together. Yes. Okay, does the vector math work out here? We have -1, -3, +3. Yep, so that works. Okay. Yeah, and we can go ahead and do the rest of these, but hopefully you get the point here. Obviously, a little more complicated because you have to add 4 versus 3 indices. Okay, but that's what we got to do with the hexagonal. Okay, so whew, all right, we made it. So that's a wrap. Thank you very much for sticking around. So if you have questions, please put them on the video for the page so then everyone can see them and benefit. Okay. I try to respond as soon as I can. Again, this is, filmed raw, unedited, unfiltered, uncut, right? Cat crawling all over me at times, whatnot. So if I can't deal with the question through YouTube, I'll ask you to email me and then, we'll deal with it that way. Okay. All right. So with that, thank you very much for all your support. And I look forward to seeing you all in the new year and wish you the best with your microscopy studies in the new year and hopefully, making more videos for you. All right. Take care, everybody. Happy holidays and Happy New Year.